about OpenConnect. OpenConnect is the CDN for Netflix. And Netflix, as you know, is a video service provider, also active here in Nigeria. So we'll talk about a little bit how our streaming is working, and first of all, a little bit about how was the internet previously and how is it today. As other people today mentioned on the stage, in the old days, internet was some global providers, some regional providers, and then the ISPs were telling internet access on the bottom. And then the data would be flowing bi-directional, but it would flow up to the tier 1s and down again to the ISPs. Today, things are looking a little bit different because we are a number of people who have a lot of traffic going in one direction, and peering have come in and bypassed the global providers. So today we have content providers, cloud providers, and internet exchanges changing the directions of the flows on the internet today. So Netflix CDN is part of this new way of a new architecture. And what we did is that we decided to build our own CDN so that we can optimize that for the Netflix service. And a quick reminder on what is a CDN. Well, a CDN is some logic, and it's a bunch of servers where you have the files that the users want to access. And our CDN works that we have all the intelligence is hosted in the cloud, as we just heard about how you can build your own cloud. We're using the Amazon cloud to have all the intelligence behind the Netflix service and behind the Netflix CDN. Then we have our own servers sitting all over the world. And when a client, so when you is having your device and you want to watch a Netflix movie, there's a communication going on between the client and the intelligence in the Amazon cloud. And then the client eventually is told, go to this server and download the movie. And then first at that point, the client talks to the actual Netflix server. This is a map of where our servers are located today. All the green dots are servers that are standalone servers inside ISP's networks, and the orange dots are point of presence of the Netflix network. This is the Netflix network that is connecting all the orange dots on the map before. And as you can see, we have one point of presence in Africa, which is in Johannesburg, and a few points of presence in Europe, and a little bit more in the US, and a couple in Asia and Latin America. So, when we have a Netflix point of presence, how can you connect to Netflix? Well, we have an IX site, and at that IX site we can connect directly or use an internet exchange, but the way we always connect is we're using a peering connection. So we had the first presentation of today was telling us about what is peering, and basically it's when we're connecting when there's a mutual interest and a mutual benefit, and that is the only way we do connect to ISPs. It can happen at an internet site, and then we send the traffic to the ISP, and the ISP then sends the traffic through their network and to the end users. Another way we can do that is still connect, if it's possible, at an internet connection site. But another way, but in addition to that, we can give the servers from our CDN to the ISPs, and they can place them locally in their own networks. And that way reduce the traffic that is hauled through the backbone and through the network of the ISP. This model can also happen when there is no IX site, but then the traffic to the servers will then go over the internet. Obviously, we can do this with mobile providers as well, and again, when we do this, the movie is just, the traffic is going the same way. we have 3 types of servers, and something went wrong with the last photo in the presentation. I'm sorry about that. But we have, in the middle server of this is a standard 2U server, what we call it, and it's filled with hard drives, with spinning drives, and with flash drives, and that is our standard building stone. Then we have what we call flash servers, which is a very high volume server where we can push a lot of bandwidth out of a very small server. We have these and those can be used when we have a very high demand, and the only storage that are used in those servers is SD drives. And then the last one that's on this slide is what we call a global server, which is a smaller version of the storage server that we're using in a low volume market. So again, so these are the 2 first ones, and we have a lot of spinning drives in the storage server and SD drives in the flash server. So the ones where we have those spinning drives, we can have the complete catalog, and the servers, the ones we're using today have a 48 gigabits per second bandwidth, and just have actually a lot of traffic and a lot of in the flash servers, we only use the most popular content. So we have analytics that are showing us which movies we pretend we know will be popular the next day. And we make sure to store those in the SD drives to make sure that the servers are as efficient as possible when we actually serve the traffic. That's about 7% of our total storage, but it's 60% of our total traffic on a global basis. So these caches that we're preventing are filling while we sleep. Because we have this knowledge about what people are watching, we have a good prediction of what they want to watch tomorrow, which enables us to actually go make sure that the movies are on the servers before there is a demand for it. So an example here is from a server where you have above the 0 line, that is the served traffic, the streaming traffic, and but below the server line is the fill traffic. So we fill during the night, when the server is not very busy serving anything, and then we have the full capabilities from the server to serve during the nighttime. So that's one benefit, it makes the servers more efficient. Another benefit is for the ISP that have this server in their network. The traffic going to the server is now going in the middle of the night, and not during peak hour, where the network is busy doing other stuff. So, to illustrate, also the whole why are we caching, we are only sending one version of the file into each network, but then a lot of people can watch it. Again, the fill window, it's a 12-hour long window during low traffic hours. And it enables us to, another benefit is because we know what people want to watch, we can also produce quite a high offload. So in many markets, we can stream around 95% of the traffic from the localized servers, and only 5% of the traffic in the peak hour will be coming from outside the network. There's load balancing helps, and again, popular content on the flash drivers, and we read and write outside of peak. Sometimes we can also have a little bit of an issue using this technology for on CDN, and that when it comes to low traffic markets. Because we want to put all the movies that we believe that somebody want to watch in that market the next day. If we're working with an ISP who have quite a low traffic volume, filling the server with those movies might be much more data than the server would actually be serving if we put a server into the network. So this is a consideration and a discussion we always have when we sign up with partners, is how much traffic do we have? Will we be sending more or less traffic into your net, more or less data into your network if we put a server there or not? And then in collaboration we figure out whether it's a good idea or a bad idea to work with networks. Sometimes we can break people's network. Finally, a little bit about what is the benefit for the quality if we are able to put servers closer to the end users. This is a study from India. In the beginning, when we were active in India, the average distance from clients in India to the Netflix CDN were around 7,500 kilometers. But over time, as we started deploying servers into India, the distance dropped down to 700 kilometers. And what we can see happening is at the same time, the bit rates, the average bit rates of the streams that people were watching in India went up as the distance went down. So we often say that for streaming, latency isn't that important, and that is very true, but it is a little bit important, at least when it comes to the difference between 7,000 and 700 kilometers. Again, on more parameters, that reduction in the distance also reduced the rebuffer sessions, and it reduced the median play delay, so the time it takes before the stream begins when you press play. Finally, I want to talk a little bit about what kind of technology we're using with our streaming. So we're using adaptive streaming, where we're trying to take the network conditions into consideration. And in reality, you can illustrate it by looking at the buffer. So in the Netflix client, we have a buffer, and the buffer is being filled by downloading on the network, from the network, and it's being entered by the streaming that occurs on the screen on the device. And the buffer level is what is monitored all the time. So if the buffer level drops too much, that means that the network cannot download fast enough to provide the data that's being played. So we swap down to a lower bit rate to make sure that we can always fill the buffer. Then the video quality becomes a little bit lower. Then the buffer starts to fill too fast. We can play more than we do, and then we switch off the bit rate to a higher bit rate to increase the quality when it's possible. So when we're looking at what quality is being streamed all the time, it is always a balance between how long do we want to wait before we start playing, what quality do we want to be watching things in, and what is the risk of having a rebuffer session. So what nobody wants, I don't want it, I'm sure you do not want to have those kind of things. Be very, very important. So we're trying to avoid that, but we also want to make sure that things start at time and that the quality we're watching is good. The last thing we're working very hard on trying to improve is the encoding. So we used to do what we call typal encoding, and we would take a movie and we would say, okay, this movie should be encoded in these different bit rates, and then we would encode the whole movie, and then for a certain resolution, we would have a fixed bit rate for the whole session, and then switch between that. At some point, we decided that's not a very good idea, so we started chopping them up into smaller bites, and then just do one piece. So we're doing it per scene now, saying this scene for this resolution should have this bit rate, and that way we are able to have a lower bit rate while still maintaining the same or the better quality. So to explain this graph, we have the bit rates on the x-axis, and on the y-axis we have what we call VMAF, but it is the video quality measure that we're using, which is a combination of subjective and machine learned quality measures that we've worked out actually works pretty well. So over time, we then use the ADC high, and now we are optimizing the VP9 as it's called, which is our latest encoding, where we are managing again to squeeze down under 500K and still maintain a very high quality. So, if we